In this video, I want to explain the setup for question 6 on the midterm. So what is the question saying? The question is saying, okay, so let's say that you have those integers k1 and k2, and k3 and k4 up to kn. And you know that they come from two different Poisson distributions. You don't know which Poisson distribution each of the k's came from, right? So let's make up a data set. So maybe the data set looks kind of like this. And maybe there is a 40 here, and maybe there is a 3, and there is a 0, and there is like a 50. Okay? So if you look at this data set, what you might think is, okay, so it looks like there's small numbers there's large numbers there, right? So you'd say, well, maybe those guys and this guy, they came from one of these distributions, and then the 40 and the 50, they came from another distribution. Okay? So, and let's add like a 3 here. So how would we generate this kind of data set? So here's the idea. You would say, okay, so you would say pick lambda equals to lambda 1 with probability pi 1. And you would say pick lambda equals lambda 2 with probability pi 2. And that would be your first step. And then you would say sample k from Poisson lambda. Right? So this is how you would come up with this kind of data set. You would say, okay, first point, do I want lambda 1 or do I want lambda 2? Let's say I want lambda 1, and I do that with probability pi 1, then I generate something from lambda 1. Then this one. I don't know, it's not a 5 yet, it's just a placeholder. Do I want lambda 1 or lambda 2? I think lambda 2, if it so happens that they do that, and that would happen with probability pi 2, and so on. This is how you would generate those kinds of numbers, right? And then once you've generated the lambda, you get the k from Poisson of lambda, so either lambda 1 or lambda 2. So for this kind of data set, what would be the right kind of lambda and pi that are plausible for this data set? Well, you would say, okay, so there is, one distribution where the numbers are kind of small, so maybe something that would be plausible is like lambda 1 is equal to, let's say, I don't know, I'm just making things up, so 2.2. For this one, let's say lambda 2 is equal to 45. And there's more small numbers than big numbers, so maybe pi 1 is equal to 0.65, and maybe pi 2 is equal to 0.35. So for those kinds of settings, for those kinds of parameters, this is a plausible data set, right? Because it could be that if those are the parameters, so you pick this guy with probability 65%, this guy with probability 35%, you would generate, something that looks like this. So let's now write down actually the probability of the data under this model. So this is the answer to kind of 6A, right? So what's the probability of the model? Well, the probability is going to be just, the probability of k1 through kn given lambda and pi. And of course, like this is just equal to the product of p ki given lambda and pi. So now we can just concentrate on computing this. So what is p ki given lambda and pi? Well, the problem is we don't know, right? We don't know, at least not yet, because we don't know which of the lambdas did ki come from. So we don't know, what to plug in here for the lambda. What can we do? Well, we can say, okay, we'll just use this trick where we'll say, well, we'll introduce a variable. We'll call the variable zi, and zi is going to be either 1 or 2. And zi is going to be 1 if I comes from, so ki rather, comes from Poisson lambda 1, and it's going to be 2 otherwise. So if it comes from Poisson lambda 2, right? So we just introduce the Zi, and if we introduce the Zi, what we can do is we can say, okay, so that's the definition. We can say, well, this thing is just equal to the sum over Zi in 1 and 2 of the probability of Ki and Zi given lambda and pi. We get to do this, right? So this is a general rule that you can do it. You can say P of A is equal to the sum over all the possible values of B of PAB. So that's exactly the same. We got to do this. So, okay, but this didn't quite help us because how do you compute the joint probability of Ki and Zi? Well, here's the trick. You would say Zi still ranges between 1 and 2. You would say, okay, so we'll condition Ki on Zi and lambda and pi, and we'll then multiply that by Zi because we want the joint, right? So this is going to be Zi given lambda and pi. So this is, by the way, the same thing as the mixture of Gaussian stuff, right? So, okay, so what is this thing? Well, this we can compute. So this is Ki given that we know Zi, right? If we know Zi, then there's no problem because if Zi is 0, we just plug in we plug in lambda 1. If Zi is 2, we plug in lambda 2 into that probability mass function. So this is just going to be Zi in 1, 2. So P of Ki given Zi, that's going to be the probability of K under lambda Zi, right? So let's just write the density function, the probability mass function. So this is going to be E minus lambda Zi, and this is going to be lambda Zi to the Ki divided by Ki factorial. This is this. And what is this? So this is Zi given lambda and pi. So what's the probability that Zi is equal to 1, that Ki came from the first distribution, given that we know lambda and pi? Well, if you know pi is exactly the probability, pi 1 is the probability that Zi is equal to 1, pi 2 is the probability that Zi is equal to 2. So this is just going to be pi Zi, right? So you just use the Zi to pick out one of pi 1 or pi 2. And then you just sum over those guys, and that's your answer. Okay? So you just you don't know the Z, so you just sum over it, and you get this. And of course, in order to get the total probability, what you need to do is you need to multiply all of those guys together.